Hi students, last session I am discussing about substrate control asymmetric synthesis. In this session I am going to explain reagent control asymmetric synthesis. Okay, in our syllabus we have two important topics. One is chiral boranes, another one is vinyl hydrates. Okay, in reagent control asymmetric synthesis, reagent is only responsible for formation of unequal amounts of stereoisomers as products. I repeat once again. In reagent control asymmetric synthesis, reagent is only responsible for formation of unequal amounts of stereoisomers as products. Okay, generally we use a chiral reagents. Then it gives equal molar of or equal amounts of R and S isomers or equal amounts of stereoisomers. Either it is anisomers or diastereomers. Okay, generally alkenes. Okay, alkenes are treated with boron hydrates in the presence of hydrogen peroxide and basic medium to give corresponding alcohols. In this reaction, you are using to achiral boron. Okay, B2H6 is a achiral boron and treated with alkene system, either is E alkene or Z alkenes. First, it undergoes hydroboration reaction to give alkyl boranes. Okay, the formed alkyl boranes on treated with hydrogen peroxide in the presence of basic medium, it undergoes oxidation reaction to give corresponding R and S isomers. Okay, equimolar ratio 50% of R isomer and 50% of S isomer. Okay, in this reaction we observe that substrate molecule is achiral and reagent also achiral, then it gives equimolar ratio of R and S isomers. It is not a asymmetric synthesis. Okay, in a asymmetric synthesis always we get equal amounts of unequal amounts of stereoisomers as products. In this reaction we get equal amounts of stereoisomers, 50% R isomer and 50% of S isomer, because achiral reagent doesn't differentiate pro-stereo center. Okay, in asymmetric synthesis we are using to a substrate molecule having prochiral center. Okay, prochiral center may be phase or ligands. Okay, prochiral centers may be phase or ligands to produce unequal amounts of stereoisomers. In case in this reaction you are using to achiral reagent boron hydrates, it doesn't differentiate the pro-stereo center, either rephase or psi-phase, either is a pro-R or pro-S ligands. It doesn't differentiate the pro-stereo center, then it gives equal amounts of anisomers as products in this reaction. Okay, we observe the mechanism. Alkene system are treated with diborane to give corresponding alkyl boranes. Okay, the reaction follows constructed mechanism, okay, to gives corresponding alkyl boranes, Okay, the formed alkyl boranes again are treated with hydrogen peroxides in the presence of basic medium. It undergoes oxidation reaction to give corresponding alcohol. Okay, in this mechanism we observe that boron addition in two phases, because the substrate molecule having two different phases, one is rephase, another one is psi-phase. Then hydroboration takes place in two phases, then it gives two different alkyl boranes. Okay, it is a chiral center, it is also chiral centers. Again, this chiral centers containing molecule undergoes oxidation reaction with hydrogen peroxides to give corresponding alcohols. Okay, in these reactions we compare the steric crowding with respect to boranes and methyl groups. Okay, in this SARS conformer, the two methyl groups and boron present in different planes in 120 degrees. Okay, present in different planes in 120 degrees. Okay, in this conformer, the steric crowding between methyl and boron. Okay, in this conformer, the steric crowding between methyl and boron is similar. then boron addition is equally to rephase and psi-phase. Okay, boron addition, okay, with respect to planes, boron addition top plane and bottom planes, and that means as rephase and psi-phase are equimolar ratio, then it gives equimolar ratio of corresponding alcohol. In these reactions we get 50% of R isomer and 50% of S isomer. Okay, reagent doesn't differentiate the pro-stereo center. Again, similarly, E alkenes on treated with boron hydrates, it gives alkyl boranes. Again, the formed alkyl boranes on treated with hydrogen peroxide in the presence of basic medium to gives corresponding alcohols. In these reactions also we get equimolar ratio of enantiomers. Okay, 50% of R isomer and 50% of S isomer. Okay, in these reactions the reagent doesn't differentiate the pro-stereo center. Okay, substrate molecule having pro-stereo center having two phases, one is rephase, another one is psi-phase. Okay, boron hydrates doesn't differentiate the rephase and psi-phase, then it gives equimolar ratio of R and S isomers. Okay, mechanism of these reactions also similar in previous reactions. Okay, in previous reactions, Z alkenes on treated with hydroboration followed by hydrogen peroxides and basic medium, it gives 50% of R isomer and 50% of S isomer. Similarly, E alkenes also are treated with boron hydrates in the presence of hydrogen peroxide and basic medium. Again, it gives 50% of R isomer and 50% of S isomer. Generally, the chiral boranes IPCBH2, IPC2BH exist into minus form and plus forms. Okay, campanile boranes are chiral boranes. Okay, campanile boranes are chiral boranes. Okay, these boranes are exist into minus forms and plus forms. Okay, that means one boron rotate plane polarized clockwise direction, another boron rotate anti-clockwise direction. Okay, hydroboration of chiral boranes with alkenes occurs from the less-handed side of the molecule via cis or syn addition, and the oxidation proceed with complete retention of configuration. Okay, that means, okay, alkenes on treated with chiral boranes, first it undergoes alkyl boration reaction. Alkyl boration. Okay, that means it gives corresponding alkyl boranes. Okay, the formed alkyl boranes again on treated with hydrogen peroxide to gives corresponding alcohols. Okay, in these reactions, boron addition takes place below the plane, then it gives corresponding alcohol, then it gives corresponding alcohol. The alcohol hydroxy group must be present in below the plane. That means in this reaction we observe a retention of configuration. Okay, boron addition takes place above the plane, then hydroxy group always present in above the plane. In case boron addition takes place below the plane, then the hydroxy group always present in below the plane. The stereogenic center of the newly formed alcohol usually has opposite chirality relative to the organoboranes. Okay, generally IPC2BH gives R alcohol plus IPC2BH gives S alcohol. Okay, I repeat once again. Generally IPC2BH gives R alcohol minus IPC2BH plus IPC2BH gives S alcohol. Okay, IPC1BH2 is selective reagent for hydroboration of E-olefins and monosubstituted trisubstituted olefin systems. Okay, IPC1BH2 is a selective reagent for hydroboration of E-olefins and monosubstituted trisubstituted olefin systems. Okay, IPC2BH is a selective reagent for hydroboration of Z-olefins. Further oxidation of organoboranes gives R alcohol in the presence of hydrogen peroxide and base. Okay, IPC2BH is a selective reagent for hydroboration of Z-olefins. Further oxidation of organoboranes to gives R alcohol in the presence of hydrogen peroxide and base. Okay, write down the reaction. Okay, it is a Z-olefin systems on reacts with IPC2BH. in the presence of hydrogen peroxide and basic medium, it gives 90% of R alcohol and 10% of S alcohol. Okay, the structure of IPC2BH. The structure of IPC2BH. Write to following structure. Okay, IPC2BH having two campanile rings. Okay, this is one campanile ring. This is also another campanile ring. Okay, it is a short representation of IPC2BH reagent. Okay, in this reagent we observe that large, medium, small groups. Okay, the olefin system on treated with campanile boranes or IPC2BH, hydrogen addition reaction takes place, then elimination of this campanile ring. Okay, then in this mechanism only observe that large, medium, small groups. Large, medium, small groups. Again, we observe the mechanism. Okay, first thing, it is a campanile borane on addition with Z-alkene systems. It is also campanile borane on addition with Z-alkene systems. Okay, Z-alkene systems having two phases, re phase and psi phase. Then reagent always addition in two phases, one is re phase and psi phase. Okay, which one is more preferable completely depends upon bulkiness of reagent. Okay, reagent having two different groups, one is medium group, large group, small groups. Okay, reagents always attach it to sterically less crowded site. Okay, in this way the two methyl groups are present in same site. Okay, the large group also present in same side or same plane. Okay, that means this transition state having higher energy when compared to this one. Okay, observe that the two methyl groups and medium group present in same plane, the large group and hydrogen atoms present in same plane. Okay, we observe the transition states. Okay, in these transition states, okay, the large group had hydrogen atom present in same planes, the medium group and methyl groups present in same planes. Okay, in this transition state, the methyl groups and large group present in same plane, the hydrogens and medium group present in same plane. Okay, again the molecule again untreated with hydrogen peroxide in the presence of basic medium, again it undergoes oxidation reaction to give corresponding alcohol. Okay, again it gives alcohols, 90% of R isomer and 10% of S isomer. Okay, the configuration of this isomer, first priority goes to oxygen atom, the second priority goes to ethyl group, third priority goes to methyl groups. Okay, priority direction goes to clockwise. Okay, then least priority group is away from the observer, then it is R isomer. Similarly, it is S isomer. Okay, in this reaction we get 90% of R isomer and 10% of S isomer. In the above reaction, the addition of boron to Z olefin to generates two transition states. Okay, it is due to Z olefin having two phases, re phase and psi phase. Okay, observe that addition of boron with alkane systems, we get two different transition states. We get two different transition states. Okay, these are the two different transition states. Okay, in this transition state, which one having lower energy, then correspondingly it gives more amount of yield. Okay, in this transition state is more stable, then it gives 90% of R isomer. Okay, then this transition state is unstable, then it gives 10% of S isomer. Okay, the formation of products completely depends upon only for the formation of products completely depends upon only stability of transition states. Okay, because E alkene or Z alkene having two different phases, one is rephase, another one is psi phase. Addition of boron to olefins with borane, rephase is sterically free. We observe that transition states addition of olefin with borane, rephase is sterically free. It produces a stable transition state having lower energy. And addition of olefin with borane in psi phase sterically ended, it produces a unstable transition state with higher energy. Due to these reasons, boron addition always prefers to sterically less ended side. As a result, addition always takes place less crowded side. I repeat once again, boron addition always sterically free. Okay, then always it gives sterically less substituted or less crowded alcohol. After addition of boron substrate, molecule and reacts with hydrogen peroxides and basic medium to gives corresponding alcohols. Okay, in these reactions we observe two transition states. Okay, two transition states. Okay, this transition state is more stable, then it produces 90% of R alcohol. It is less stable, then it produces 10% of alcohol. Okay, again hydroboration of E olefins. Again, previous reactions, the hydroboration of Z alkenes, it gives 90% of R isomer and 10% of S isomer. Okay, in this reaction, hydroboration of E olefins. Hydroboration of E olefins is not an enantioselective reaction. In these reactions, we get equal amounts of enantiomers. The reaction carried out in the presence of non-polar solvents and hydrogen peroxide. Hydroboration of E olefins with IPC2BH hydrogen peroxide to produce R and S alcohols. The yield of the R isomer is more when compared to S isomers. Okay, again E alkenes are treated with boron hydrates followed by hydrogen peroxide in the presence of basic medium. It gives equal amounts of enantiomers. But the same molecule E olefins are treated with IPC2BH in the presence of hydrogen peroxide and base to gives unequal amounts of stereoisomers as products. In these reactions we get R alcohol and S alcohol. Okay, 56% of R alcohol and 43% of S alcohols. Okay, E olefin system on treated with E olefin system on treated with IPC2BH. It undergoes hydroboration reaction to give alkyl boranes. The formal alkyl boranes are treated with hydrogen peroxide in the presence of basic medium to give two different alcohols. One is R alcohol 56%, another one is S alcohol 43%. Okay, in these reactions we get two different alcohols. Okay, next we study the mechanism. Okay, in this mechanism, first thing, capital boranes IPC2BH undergoes addition reactions with olefin system. It produces two different transition states. Okay, one is transition state 1, another one is transition state 2. Okay, we observe that in transition state 1, the large group and hydrogen present in same planes. Large group and methyl group present in same planes. Okay, that means in this phase having more steric crowding when compared to this one. Okay, observe the two different transition states. Okay, transition state 1 having less steric crowding when compared to transition state 2 with respect to large group and methyl groups. Okay, then further oxidation with hydrogen peroxide and alcohol, it gives 56% of R isomer and 43% of S isomers. Okay, in this reaction we observe that the two methyl groups. Okay, we compare the whole molecule. Okay, we compare the whole molecule. Okay, large group hydrogen methyl, hydrogens. Okay, we compare the whole group. The steric crowding is similar in transition state 1 and transition state 2, but in this transit state, the large group and methyl group having some far distance. Okay, in this transit state, the large group and methyl group are nearer to each other. Then this transit state having higher energy, slightly having higher energy than this one. Okay, the further oxidation with hydrogen peroxides in the presence of basic medium, it gives two different alcohols. One is R alcohol, another one is S alcohol. Okay, in this reactions we observe that R alcohol is nearly 56% and S alcohol is nearly 43%, because the whole molecule, compare the steric crowding is similar. Okay, then it gives nearly equal ratio of enantiomers as products. Above the reaction, the hydroboration of Eve olefins with IPC2BH to produce the two different transit states. It is due to presence of rephase and psi-phase. Then addition of boron always refers to rephase of the olefin. In this hydroboration reaction, transit state 1 is more stable than transit state 2. As a result, we get R isomer is more when compared to S isomer. Once again, in these reactions, E alkenes on addition with IPC2BH, it produces two different transit states because Eve olefins having two different phases. One is rephase, another one is psi-phase. Okay, then it gives two different chiral alkyl boranes. Okay, the two different chiral alkyl boranes are treated with hydrogen peroxides in the presence of basic medium, then it gives corresponding alcohols. We observe that we get two different alcohols. One is R alcohol and another one is S alcohol. Okay, in these reactions we get two different alcohols. One is R alcohol and another one is S alcohol. Okay, we observe the two different transit state 1 is more stable than transit state 2. Okay, then it gives 56% of R isomer and 43% of S isomers. Okay, next topic is reaction with S binyl hydrates. Binyl hydrates. Okay, binaphthyl aluminum, lithium aluminum hydrates. Okay, binaphthyl lithium aluminum hydrates. Okay, these hydrates are used to reduction of carbonyl compounds into alcohols. Okay, these are the highly selective reagents to reduction of carbonyl compounds into alcohols, preferentially to produce a selective enantiomers. Okay, generally lithium aluminum hydrates, it is a chiral reagents which on reacts with carbonyl compounds, it produce equal amounts of enantiomers products. Okay, reduction with lithium aluminum hydrates and unsymmetrical ketone to gives a racemic mixture of tertiary and secondary alcohols, because lithium aluminum hydrate is a chiral reagents and approach the hydrogen both phases. Okay, both rephase and psi-phase stereogenic center of hydrogen donor reacts with an anisotropic ketone to produce enantiomers. Okay, in this reaction we observe that lithium aluminum hydrate is a chiral reagent. It doesn't differentiate the posterior centers. Okay, then it gives equal amounts of enantiomers as products. But binyl hydrates is a commonly used an asymmetric reduction reagent used for the reduction of carbonyl compounds. Okay, binyl hydrate is a commonly used asymmetric reducing agent used for reduction of carbonyl compounds. It is derived from optically pure binaphthyl ethanol and aluminum hydrates. Okay, binyl hydrates or binyl hydrate and S binyl hydrate is highly enantioselective reagents. Okay, reduction of carbonyl compounds with S binyl hydrates to gives S alcohol. Reduction of carbonyl compound with R binyl hydrate to gives binaphthyl aluminum hydrates. Okay, reduction of carbonyl compounds with S binyl hydrates to gives S alcohol. Reduction of carbonyl compound with R binyl hydrates to gives R alcohols. Okay, first in preparation of optically pure binaphthyl on reacts with lithium aluminum hydrates in the presence of ethanol to gives binyl hydrates. Okay, in this reaction first optically pure binethyl alcohol on treated with lithium aluminum hydrates in the presence of ethanol to give corresponding binyl hydrates. Okay, we observe that binyl hydrates on treated with unsymmetrical ketones, it gives corresponding alcohols. Okay, S binyl hydrates always gives S alcohols, all binyl hydrates always gives R alcohols. Applications of binyl hydrates. Okay, first acetophenone on treated with S binyl hydrate. Okay, S binyl hydrates to gives S alcohol. Okay, acetophenone again on treated with R binyl hydrates is gives R alcohols. It is a highly anisotrophic reagents. Okay, highly anisotrophic reagents. Okay, unsymmetrical ketones on reacts with S binyl hydrate, it gives S alcohols. Unsymmetrical ketones on treated with R binyl hydrate, it gives R alcohols. Another example, ketones. Okay, ketone on treated with R binyl hydrates, it gives R alcohols. Okay, we take any examples. We must take unsymmetrical ketones on treated with S binyl hydrates to produce S alcohols. Okay, R binyl hydrates produce R alcohols. Okay, it is a highly anisotrophic reducing agent, S binyl hydrates and R binyl hydrates. There is no any specific mechanism for binyl hydrates. Okay, there is no any specific mechanism in this binyl hydrates reduction reactions, because it is a reagent control asymmetric synthesis. It is also a catalytic reductions. There is any specific mechanism. Look at the transfer of hydride ion either rephase and siphase, because we are taking it takes a unsymmetrical ketones. Unsymmetrical ketones having two different phases. One is rephase and another one is siphase. Okay, hydride ion transfer to either top phase or bottom phase, or rephase or siphase. It gives corresponding alcohols. Okay, in this reagent we observe only one thing. S binyl hydrates always gives S alcohol. R binyl hydrates always gives R alcohols. Okay, in posterior center either rephase or siphase. Okay, rephase undergoes addition reaction. Okay, rephase of a substrate molecule undergoes addition reaction. Either it gives R isomer or S isomer. Okay, siphase of substrate molecule undergoes addition reaction with nucleophile. It gives R alcohol or S alcohols. Okay, then only as well that S binyl hydrates gives S alcohols. R binyl hydrates R alcohol. We must take a